Good morning. Okay, so we were discussing about these extension headers of IPv6, right? So these are all extension headers like off by hop option header, fragment header, routing header, right? So I discussed this that hop by hop option header you can pad with 1 byte. Okay, you can pad 2 bytes, or you can, whenever it is more than 6553 byte, you can use a jumbo payload, right? And router alert, uh, that the contents of two routers, it is basically used for setting reservation. I told you, like how a reservation is to be made by a protocol named RSVP. So this is basically helps in making reservations at different routers coming in the path. So that is RSVP. So this is hop by hop options. And fragmentation header, already we talked about that there is a fragmentation offset that says the position of a fragment in a original datagram. Then there is a identification unit, so that says basically the data length. Okay, so all those things comes under this fragmentation header, more flag, right? So all that comes under this more flag, and you should remember that in IPv6 the fragmentation is done by the source only. It is not done by the intermediate routers like in IPv4, right? Because the issue with in IPv4 was observed that because as the datagram passes by in the network and it visits each router, the router fragments it further. So once it reaches at the destination, so the original datagram is divided into multiple fragments, though it is not required, right? Then also it gets fragmented and gets smaller and smaller. So more number of fragments, right? So in terms of overhead, like it is more, and the second issue, like that there will be more fragments, right? The destination has to wait for a longer period of time to for reassembling them, right? So that creates delay in delivery of the data, right? So now in IPv6, this job is being taken care by the source itself. So how the source fragments the packet before, how does it know about that? What are the networks involved during its transit from this station to the destination station? It simply sends some frames, right? As I said, the route recording is done. So while does the route recording, it abstracts the information of all the networks, that what are their maximum packet size limit, right? That they can allow. So it collects the information, and based on that it fragments it, right? So, and the routers can't fragment the datagram further, right? Just a minute, huh? Hello. So it even though it is so it collects the information about the networks and fragments it. but in case if the network packet size limit is uh, smaller as per the fragment as compared to the fragment size, router cannot fragment. In that case, the router has to drop that fragment, right? It cannot forward it further because its size is higher than the maximum size of the network. So in that case, the router has to drop it, right? So these are the fragmentation header fields. Next header, reserved, fragmentation offset, which is the original position of the original datagram or of the fragment in the original datagram. Reserved, more flag, indicating more fragments are there. Identification, like this is what the data unit identifier, or you can say the identification field says about the data length and other things, right? Routing header, right? Routing header includes, as I told you, that it can be a fixed routing, strict routing, we can say strict routing or fixed routing, or loose routing or dynamic routing, or there can be a source routing. Like all the options are there. So what is there in the routing header? Routing header consists of the list of nodes, right? List of intermediate nodes to be visited, because uh, it contains the routing information, like how the datagram will move in the network. So in order to do that, it contains the what are the nodes to be visited. Okay, the next header means the protocol information, right? Then the header extension length. What is the header length? In the routing type, whether it is fixed routing, dynamic routing, or the source routing, and how many segments left means how many numbers of nodes still to be visited. So this is the information in the routing header, and there is a provision for route recording and other things also, that also falls under the this routing header, right? And there is a destination option. As I told you that there is a destination option. It is similar to hop by hop option header. Only difference is in a hop by hop option header, the datagram, the information is passed to each intermediate device, right? Each router, right? While in a destination option, uh, the information is intended only for the destination. No intermediate device is allowed to see the information, right? So then there is a ICMP version 6. As we were discussing with IPv6, there is an ICMP version 6, because IP, as you know, it doesn't provide any guarantee, right, of delivery, no error, no flow control. So at usual, it provides the best effort service, and to encounter or to report problems in the network or to generate feedbacks, right? Whenever something wrong happens in the network, in terms of messages, as we saw ICMP v4 that was associated with ICMP version IP version 4. Similarly, we have an ICMP version 6 which is used with IPv6. So some of the messages remain same except few changes in ICMP v6. Okay, so once again there are two types of messages: query messages and error messages. So in the error messages, if I say you had earlier destination unreachable, redirection, parameter problem, time exceeded, right? These these messages were part of IPv4 as well. Okay, which which one is missing? Can you say which one is missing over here in ICMP v6? Which message is missing in ICMP v6? Which was a part of IPv4 but not here? If you remember, there was a source quench message. Source quench message was used for flow control. Okay, So source quench is removed in ICMP v6. Okay, source quench is not no more existing in ICMP v6, and the source quench message was used basically for flow control, because whenever the router was unable to withstand with the excessive flow coming from the source, right? The router has to request the source that please to slow down, so that the router starts dropping the packets, and in response to that it sends a source quench message towards the source informing that because the flow is excessive, and that is the reason of dropping the fragments, right? But in why it has been removed in ICMP version 6, because you can see here that all the information related to all intermediate routers and other things are already existing with the source, right? The source is well aware of the number of what is the buffer size at the router and other things. So this source quench message was not required in ICMP version 6, right? And in place of this, another message was added, that is packet too big. Because why this message was added in ICMP v6? Because here the fragmentation responsibility lies with the source only, right? So if the source fragments the packet and the router is unable to forward because of the fragment size is larger than the network's permissible limit, then in that case the router drops the fragment and sends a message that is packet too big. So that indicates that further fragmentation is required. A source has to further fragment the packet and then send, right? So packet too big is added in place of source quench in the error messages. Okay. Then, as I told you that as far as the query messages are concerned, there is a echo request and echo reply message. They are still there, right? To check the existence of the other party, echo request and echo reply messages are there to open a connection between the other party, right? But this address mask request and reply messages were removed in ICMP version 6 because here there is no subnetting concept is not here. So this mask request and reply messages are dropped. Timestamp and reply messages were hardly used earlier in ICMP version 4, so they are also dropped, right, in ICMP version 6. So this is what about ICMP v6. Then another important topic like that is, see, we all have seen the migration from IPv4 to IPv6, right? So, but there may be a cases that how the migration will take place, right? How the transition will take place from IPv4 to IPv6. Because there may be a chance that either suppose all are not migrated to IPv6, some of them are still using IPv4. And in that scenario, if how a IPv6 user will communicate with an IPv4 user or vice versa. There may be a case, this is the first thing, that how an IPv6 and IPv4 user will communicate with each other. Second thing is that the two IPv6 user wants to communicate, but the network portion from which the packets will travel, okay, that area uses IPv4, okay, or the otherwise the two IPv4 users, right? Like two IPv6 users are here, and this area where this portion of the network from where the packets are to traverse, this area here the users are IPv4, right? where IPv4 users exist. So how this will be done, right? Or then there are three ways were suggested that we can do in three ways. The first one is a dual stack, right? Dual stack means at the network layer, the user will have both IPv4 and IPv6 both, right? It will have both IPv4 and IPv6. So depending on the requirement, the user will use either IPv4 or IPv6, right? जैसे आप करते हो ना कभी कभी सिस्टम में, you have a Linux also, you have Windows also, right? Both the OS you can have. Similarly, on the same ground, there will be two IP versions will be there at the network layer, IPv4 and IPv6, and a user can use anyone as per the requirement, right? The other option, other thing that I said about tunneling is useful when you have two IPv6 users separated by a network which is owned by IPv4 users, right? So it acts like a tunnel to this IPv6 user. So the packet originating from this IPv6 user will be encapsulated in a IPv4 header, right? In a IPv4 header, and then it travels over in this tunnel, just like a tunnel. The train enters into the tunnel and then leaves out. Similarly, a packet will enter into this region, IPv4 region, and will leave out from here. So while it is entering into this IPv4 region, it will be encapsulated in an IPv4 header, right? And once it leaves out of this tunnel, this encapsulation will be removed. Okay, and then IPv6 header can be seen by this IPv6 user, and the packet can be delivered to this IPv6 user, right? You following that how what I'm saying, that the two IPv6 users separated by a network that is owned by an IPv4 users. So these IPv4 users, so a packet originated by this IPv6 user will be, because it will be having an IPv6 header. So what are the differences in header differences? If you compare, an IPv6 header is of the source address and destination addresses are of 128 bits. Okay, type of service field is replaced by a ECN and apps field. Okay, priority field, flow label field is there. Then total length is replaced with a payload length, right? Like that, there are many changes. The headers, the fragmentation, offset, and other things are now part of the optional header. They are not part of the base header. So there are many changes in the headers, right? So first, an IPv6 packet needs to be encapsulated in an IPv4 header, and then it travels over here. Then at this point, when it leaves the IPv4 region, it removes that IPv4 header, and then it is suitable for IPv6 user. And the third possibility is that you need to perform a header translation, and header translation will be done because if your 90% of users are IPv6 and 10% of users are IPv4, then in that case you need to perform the header translation, right? It can be done easily, right? But it requires a lot of like your routers must be capable of doing it, because like 128 bits address needs to be converted to the 32-bit address, right? So what we do, we generally take the rightmost 32 bits of that, and the remaining bits are dropped. Similarly, other fields, it is given in Forozen, right? Like this traffic class field, which was earlier type of service field, right? Flow label will be discarded, right? Because there is no flow label in IPv4. Hop limit is to be converted to a type 2 lib field, right? So protocol, total length, and this are now the optional header are now part of not the base header. So conversion is required. Each field needs to be converted to an so header translation is to be performed, right? So now the next part of this module is internetworking operation. So in this internetworking operation, we will discuss that what is unicast and multicast routing. Okay, unicast routing, you know. So here, internetworking operation, we will be mainly discussing about the routing protocols used at the network layer, right? And then the quality of service models. So as you are well aware that what is multicasting? Multicasting refers to a group of hosts or on one or more networks. So it has many applications like multimedia broadcast, teleconferencing, databases, like the shared databases you want to access with a group of persons, distributed computing, real-time work groups, right? So these are the applications of multicasting. So how this multicasting and what is the difference in broadcast and multiple unicasting? As I told you that broadcast is not permitted. So it can be considered as a broadcast like multiple unicast. I told you earlier that there is a unicast, multicast and multiple unicast. Okay. So you can see here that these are the different networks. Network 1, network 2. These are the routers A, B, okay. Connected C, D. These are the routers. This is the multicast server. It's a group member connected on network 3. Okay. So like that, there are different group members connected on different networks, right? A multicast network. This is a network 4. This is a local network LAN 1, LAN 2, LAN 3. Okay, LAN 4, LAN 5. Okay, so so these are connected through routers. Okay, this is another network. You can say a communication network. So all that. So how this works, right? You can see broadcast a copy of each packet to each network in the configuration. So when you are sending, okay, from the source to and to, this is a broadcast, multiple unicast and multicast. So you know that in what is the difference? The difference in broadcast means how many copies will be generated. There will be total for such a scenario when you are sending a packet from suppose from a user in group network 3, right? Um, and how many pack copies will be generated in that scenario? In multiple unicast means like you will be sending a mail to 5 persons, right? And you same mail to 5 persons, and you will be adding the email ID of all the 5 persons separately. So that is what multiple unicast. You will be sending the same message to 5 different persons, right? And multicasting means like same message to a group of persons. Are you following? Like in a multicasting, you will be sending a mail to your EC group. So that means you will be sending a single message copy to your group because all the members are existing on that group. But in multiple unicast, multiple copies are created at some time difference. Okay, by from the same source. And in broadcast, number of copies are created Okay, so so obviously the load generated by multicasting is less as compared to the broadcast and uh, multiple unicast. Okay, so you can see here that so the multicast server on this network N1 is transmitting packets to a multicast address that represents the workstation indicated on network 3, right? Network 5 and network 6. And the server doesn't know the location of the members of the multicast group. The server is supposed to send a message to a multicast group whose members are available on network 3, network 5 and network 6. But it is unaware of the location of the group members. So only one way to assure that the packet is received by all of the group members is to broadcast a copy of each packet to each network, right? So that it will broadcast. So one packet it will address to network 3 and would traverse N1 link L3 and then it will be delivered over here. So the router B, this router B is responsible for translating this IP label multicast address to a MAC label. So it has to be delivered on this network, right? So to a MAC label multicast address before transmitting the MAC frame onto N3. Okay, so like that, if you see here, that what is the difference? Basically, we are just studying that what is the total traffic generated by a broadcast, multiple unicast, and multicast. So if you see that in order to send a packet, okay, from the source to N2, because if you see here, what is the source? Source is this. So to send it to N2, okay, how many copies are to be generated? It will generate a copy and it will be given to this link, right? And then it will be delivered to this. So through L1, so how many copies are to be generated? One copy will be generated by at N1 and then one copy will be generated at L1. So from source to N2, it requires two copies. Source to N3, how many copies are required to be regenerated? So three copies of the same message. So like that, the total number of copies required to be generated when you are saying a broadcast, it will result in 13 copies of the same message. When I talk about multiple unicast, the total load generated will be of 11. When I say multicasting, it reduces to 8, right? So you can see that the multicasting reduces the load. So basically, how this multicasting works in reducing the load. Because if you remember, we talked about the spanning tree. So a least cost path from the source to each network, basically that includes the member of each multicast group, is determined. So that gives us, so when we determine the least cost path from the source to each network on which the members of the multicast group exist, that results in a spanning tree. Okay, that is basically provides us the least cost path and it results in a spanning tree. Okay, and once we get that spanning tree, so as you know, the source transmits a single packet along the spanning tree, right? Like that. Okay, this is an example. So once you determine the uh, spanning tree from source to multicast group, like from network N1, right? This is router D, this is router B, network 3. So how many total? So once you have got this, this is what a spanning tree. There is no closed loop exists. You can see here, right? So how many packets are generated? So you can see here that all the closed loops are, this is for the multicast transmission. How many packets are generated? So the source transmits a single packet along the spanning tree, okay, and it gets duplicated by routers only at branches. So once it comes over here, it gets duplicated over here at the branches, okay. Ek, do. So you can see that how many copies will be generated. So the source transmits a single packet from N1 to router D. D makes 2 copies, one through L1, one through this L3 and L4. B receives the packet from L3 and transmit it on N3, where it is read by the member of the multicast group. Okay, and this L4, this router C regenerates to both E and F, in order to deliver to both E and F. This then C would only need to transmit one instance of the packet for both routers to read. So it will transmit one copy, so it reaches to both, right? So this is how we done the multicasting, and multicasting results in less load. So what are the requirements for multicasting? Because when we talk about a unicast transmission, the job of a router is very simple. So the routers, because this unicast address represents only a single destination on the network. But when we talk about because the router's job is simply to forward the datagram using the shortest path to the destination network. But with multicast transmission, the routers are required to forward 2 or more copies of an incoming datagram. Okay, and this multicasting is not that easy, because finding out the shortest tree, because the group members may be scattered, okay, over because if the group members are scattered on different networks, right, it is not very easy to perform multicasting. Multicasting is a very complex job, okay, especially when the group members are scattered on different networks. So first of all, we need a convention to identify a multicast address. As you know that in class D, in IPv4, the class D addresses were reserved for multicasting. So you can easily identify the class D address and say it's a multicast address. But in IPv6, as I told you that there is a 8-bit prefix, all ones, okay, 4-bit flag field, 4-bit scope field, and 112-bit group identifier is there. Out of 132 bits, 128 bits, okay, there is a 8-bit prefix, all ones, 4-bit flag field, okay, 4-bit scope field, and 112-bit group identifier. So 16, 20, and 8 bits, 128. So 8 ones in the beginning, 4-bit flag field, that says basically it's a it's a permanent address or it's a temporary address, like that. So that 4-bit flag field says about the characteristic of that user, and 4-bit scope field followed by a 112-bit group identifier. So there is a 112-bit group address. Okay. So this flag field says about whether the this address is permanently assigned or not. The scope field indicate the scope of applicability of the address, like from a single network uh, to a global networks, right? When you are transmitting the packet from a source to the other part of the network, the nodes, especially the routers, which are routers or source, which are participating in this routing algorithm, they must be capable of translating the IP multicast address into a list of networks containing group members. As you can see over here, that this router B must be capable of translating a multicast address into a network address. Suppose this is an Ethernet LAN. Okay, so this IP multicast address, because the packet which is received by router B, because the router works at the network layer, so it is basically an IP multicast address. So that IP multicast address needs to be converted into a network address. Network address, suppose if it is an Ethernet LAN, it needs to be converted into an Ethernet address, right? So 128-bit address needs to be converted into a 48-bit address. So the router must be capable of translating that address into IP multicast address into a network address, so that it can deliver the information to the group member connected on this network, right? So this allows the node basically to construct a shortest path tree to all over the networks containing group members. So generally some of the multicast addresses, okay. So I hope this point is clear.
Yes, sir.
The routers, so some of the multicast addresses may be assigned permanently, some of them may be assigned dynamically. Okay, that individual host may join and leave multicast group dynamically. तो अब how will you keep a record? जैसे मान लो ये क्लास हो रहा है, right? So some of the members or suppose some live, some Facebook live is there. Okay, so you do not know how many members will be connected on that, right? Or how many members will not connected on that. So there can be up some multicast addresses may be assigned permanently. Generally, the multicast addresses are generated dynamically, because you do not know that the individual host may join or leave multicast groups dynamically. ऐसा होता है ना, like you joined some group, then you left it, okay, and then you join another group. So some mechanism is required to keep track of the number of members in a particular group. Okay, so there should be some mechanism that is required uh, so that you can keep track of the number of members in a particular group, because the membership is dynamic. Host may join a particular group or may leave it in at any time. So suppose if this host, this group member is a part of this group, but it leaves the group and become a member of another group, right? Then this packet should not be delivered to this group member, because it is no more a member of this group. So in that case, keeping track, and if suppose this is not a member of this group, so now on this network N6 there is no member of the group, then in that case The packet should not be routed to this, right? Because this membership is dynamic in nature. Okay, so in such a scenario, some mechanism is required. So that is basically taken care by a protocol named IGMP. It's called as IGMP. Internet Group Management Protocol. Are you following or not? Like on a particular network, some group members are there, but those group member may leave that group and may not be a part of the group. So they may not be available on that network. So updated list should be available. So a mechanism is required for host to join and leave multicast group. So there should be a way that if a host joins a particular group, it should inform the routers, multicast router, that I join a group, I'm joining a group, and once the host leaves a group, it informs the multicast router that I am now leaving the group, no more communication from your side, right? So that provision is required. So in that, how it is basically done? So routers must exchange information. Routers exchanges two types of information. First is which networks include members of given group. Suppose EC group है. So the members are available on which particular network. Okay, some members may have joined, some members may not join, right? Some members may leave. So which networks include members of given group? जैसे हमारा जो क्लास चल रहा है, this is also an application of multicasting, right? Presently, maybe all of you are not in the campus, so in that case, you are a part of a different networks. You are connected through different networks. So multicasting means like where you are connected, the packet should deliver to that particular network, right? So how it is done? So routers exchange information that where exactly, because some of the members, मान लो class में there are 56 students, but generally 31 students or 32 students are coming, remaining are not coming, but sometimes they may come. So in that case, you have to figure out that how many members are joining, how many members are not joining, and the information should be propagated to them or not. So which network include members of given group? Sufficient information to work out shortest path to each network. Okay. Sufficient information is required to find out the shortest path to each network. We need the routing algorithms to work out shortest path, because the routing algorithms are there to determine the shortest path between source to each network. So the routers must determine routing paths based on the source and destination addresses, right? This is shown that from router C, how you can connect through multicast group, all the members, right, from router C, the same network. From router C, how will you connect to different networks, the members? So router C has been taken as a root router, and from there the shortest path tree is designed. So I told you about the IGMP that takes care of the membership, because the membership may be assigned dynamically. Individual host may join or leave a particular group at any instant of time. So there is a protocol IGMP, Internet Group Management Protocol. Its main objective is whenever any host wants to subscribe or unsubscribe a particular group, they need to inform the multicasting router. So IGMP currently it is at version 3. Initially, when IGMP was introduced, okay, in the beginning, so there were some limitations of IGMP, right? So IGMP is used by hosts and routers to exchange multicast group membership information over a LAN. Okay, so IGMP exploits the benefit of the broadcast nature of a LAN. It is used by hosts and routers to exchange information about the multicast group, and it basically exploits the advantage of the broadcast nature of the LAN to transfer information among multiple hosts and routers, right? So it supports two operations. Hosts can send messages to routers to subscribe and unsubscribe from the multicast group, and group will be defined by the multicast address. Okay, which particular group you want to join. So the host needs to send this information to the router in order to subscribe and unsubscribe a particular multicast group, and that can be done by which group will be identified by a multicast address. So routers check which multicast group of interest to which host, right? So based on the information received by the router, they determine that these are the members on these networks for a particular group, and routers periodically check that which multicast group are of interest to which host, right? Routers are supposed to check periodically because in order to keep a track, मान लो आज कोई member है उस group का उस network में, and suppose next day it is not there, right? So it needs to be periodically checked whether the members are available on a network from a particular group or not, right? So IGMP is currently at version 3, but when IGMP was introduced at version 1, the host could join group. Okay, the host could join group, but they were not allowed to unsubscribe from the group. They can join any group, but they were not allowed to unsubscribe from the group. So in earlier, routers use timer. Basically, the routers use timer. They used to keep timers for how long this particular host will be a member, and after that, once the timer expires, they unsubscribe the members. So host could join a multicast group, but they are not allowed to unsubscribe it. Moreover, once you become a member, you will receive transmission from anyone else on the group. If you do not want to receive, it was not in your control, right? Then it was modified in version 2. Receivers have to subscribe to groups. Are you following? The host could join group. Routers use timers to unsubscribe members, but receivers have to subscribe to groups. Sources do not have to subscribe to group. तो जब आपको source का पता ही नहीं होगा, then multicasting will be very difficult, right? You do not know where exactly you should start building the spanning tree. So if the source is missing, you cannot construct a spanning tree. And moreover, any host can send traffic to any multicast group. So the problem was spamming of multicasting group. Even application label filters drop unwanted packet. They consume valuable resources. So establishment of distribution trees is problematic because the location of sources is not known. Okay, host can subscribe. Okay, receivers have to subscribe to the group. Sources do not have to subscribe to the group. Any source can send a message in the group, and it will be received by all the receivers, right? So the position of the sources was not known, So it was problematic while creating the distribution tree. So finding out globally unicast multicast addressing was difficult. So in IGMP version 3 allows host to specify list from which they want to receive traffic, right? So filtering is added in basically IGMP version 3. Filtering capability is added. So now a receiver can decide whether I want to receive a packet from this host or not, right? The sources are also subscribed to the group. So now since we know the position of the sources, we can figure out the spanning tree, the shortest path tree, right? So इसके आगे का हम लोग next class में करेंगे. And next week there will be a second quiz, right? Okay, thank you.